Welcome to module 3 of the course Time Dependent Quantum Chemistry. In this module, we will go over translational motion, a free particle moving in one dimensional space, and how to represent the quantum dynamics of a free particle. One of the simplest forms of motion is perhaps a free particle traveling in one dimensional space, and a classical picture of such particle moving in one dimensional space is given here. I have a space, one dimensional space, and generally we represent a particle by a ball like this, and it is moving, it's translating. The potential experienced by the particle is 0 because it is free particle. That is why V potential is 0. Everywhere in space, and classically this particle moves at constant velocity because there is no potential. That is why it will just move without any restriction and will have a constant velocity, and classical velocity is given by momentum by mass that we are familiar with. But if I want to represent this classical idea, free particle moving in one dimensional space in quantum mechanics, this problem needs to be described using the time dependent Schrodinger equation, and we can write down TDSE equals Hamiltonian operator, where Hamiltonian operator will be given for the free particle. It is going to be only kinetic energy part, potential part is 0. That is why we have this is 0. That is why we have removed potential part for the free particle. And we have this TDSE. So, this is the TDSE which needs to be solved for free particle, where this wave function is called particle wave or matter wave. So, what we are going to do here is that the moment we come to this quantum mechanics view, there is nothing called particle in quantum mechanics. In quantum mechanics, although we can name it as a particle moving, but it is not exactly like a ball moving or like a point moving, which we generally perceive from classical viewpoint. So, what is the picture of a particle in quantum mechanics? It has a mass, definitely it has a mass, but it should look like a localized wave. This is an advanced information I am giving. I am going to prove that, but the reason why I am giving this advanced information immediately is because this will give you the correct picture of a particle in quantum mechanics. So, we will never imagine that in quantum mechanics I have a particle of mass m like this. This is a wrong picture because it is represented by particle wave, more specifically localized matter wave. This localized matter wave is actually a particle in quantum mechanics. It is localized in space, in position space. So, we will prove this. How do you know that? But this is a localized wave in quantum mechanics. So, let us begin. Let us start with this solution of TDSE, and because we have no potential, which means potential event does not depend on time. So, there is no potential, I can use the variable separation method, and if I use variable separation method, immediately I can write down the form of the solution would be like this: e to the power minus I E t by h hat, where E represents kinetic energy of the free particle, and it can be anything. A free particle can have any kinetic energy, and depending on the kinetic energy my solution will vary, because the phase factor will change. So, as usual, what we do, we insert this solution to the TDSE. That is exactly what we have done always, and if I insert it, then immediately I get time independent Schrodinger equation, which will be given by h cut square by 2m, second derivative psi x equals E psi x. Note that here I have used partial derivative and here I have used total derivative, because it depends on only x, and here psi depends on both x and t. So, what is the solution of this? I can have a solution of following form: psi x equals, either I can take this solution e to the power I k x, what is k I will present it, or I can have a solution like e to the power minus I k x. These are the two solutions I can have. A and B are constants, and I can get these constants from normalization condition. And we can prove very easily that if I know the kinetic energy of the particle, I will be able to get to know k as well. So, k is going to be square root of 2 m e by h cut square. I can prove that if I plug this form into this equation, what I get? I get A I k e to the power I k x. This is the first derivative, then I have to go for second derivative as well, and I have h cut square by 2m. This is which is nothing but e to the power a e to the power I k x. So, I get the second derivative, a I k whole square e to the power I kx equals Ea e to the power I kx. Aikx is cancelling out. So finally I get h cut square k square by 2m equals E, or this k equals 2me by h cut square. So if I know the kinetic energy of the particle, if I know the mass of the particle, I will be able to get the k. This is called wave number. It is related to the wave vector of the particle, because it is, and when each time I am using particle, but remember it is not like this. What is the actual form of that particle in quantum mechanics, that will be presented very soon. So I said that there are two forms I can have, these two forms I can have, and if I have these two forms, what does it mean by these two forms of solution? I can try to find out by taking the momentum operator acting on them. Momentum operator I h cut ddx a to the power I kx. I am considering the first form. I get minus I h cut I k a to the power I a kx. It is giving me h cut k, but positive. This is psi. So the magnitude of momentum is going to be h cut k. H cut k, because it is positive, momentum positive, which means it is representing a particle. What is the form of the particle we will get to know, but representing a particle which is moving along positive x direction. Similarly, one can show that this form psi equals b e to the power minus I kx, this form is representing a particle. Actual shape of the particle is still unknown, but we are just encircling the whole word, the whole word, and then showing it is moving in negative x direction. So these are the two different form of the particles. Either way it is moving, and that is the representation of these two solutions. Let us assume that our particle, the particle is moving along positive x direction. In that case, I will be able to consider psi x equals a e to the power I kx. This is the solution, and as a result I will be able to write down the total wave function, space and time dependent wave function, to be like this, where we have seen that E equals h cut square k square by 2m. That is the kinetic energy of the particle. And if we look at, if we recall our, we represented the plane wave, electric field of the plane wave, we represent it like this way, E x t, not x, it was omega, E, yeah, x t equals E naught e to the power I omega naught t minus k naught z. Sorry, this was z. Yeah. That is the way we have represented in the first module. We have represented an optical wave, a plane wave, and note the similarity between these two. So, this is your matter wave and this is your optical electromagnetic wave. Eventually, they are showing the plane wave form of the wave function for the particle. So, the particle is represented by the plane wave for the time being, and we will see whether this is possible or not. But one thing we have already learned from when we have presented electromagnetic wave, that everything within this exponential part is called the phase function. And the phase is important because if I get to know the phase, I will be able to get the velocity. Phase will give me the velocity information. So, how can I get that? Phi total phase is kx minus Et by h cut. And the definition of phase velocity, what is the definition of phase velocity? Phase velocity is defined as the velocity of a constant phase front. That's the definition of phase velocity, a constant phase front. And how do I plot this? This is a complex form of the real part. So, this real part will be given like this way, cos kx minus Et by h cut. This is like this, and we see that this is a time. After each particular time, this particular phase is repeating, and that is called constant phase front. So, if I could ask this question, with what velocity it is repeating or with what velocity it is propagating, that is the constant phase front propagation. And for that I need to make the first derivative to be 0. Constant phase front, it is going to be, for the constant phase front, the first derivative is going to be 0 with respect to t, and that is why we get dt minus E by h cut, which is going to be 0. So, dx dt equals now E by k h cut. We know E equals h cut square k square by 2m. If we plug that in here, I get h cut square k square by 2m h cut, which is nothing but this equation. So, we get the phase velocity of the particle. Particle velocity I can get from this wave function. So, this particle which is moving has a velocity which is called phase velocity h cut k by 2m, and so far the particle, how does it look like? It looks like a plane wave, a wave propagating through space. Now, if this is the picture of the particle, of the quantum particle, we have many issues, many strange behavior we will be able to find out immediately if I consider this to be a solution for the free particle. And what are the strange behavior we have already? Let us understand the meaning of this wave function and how does it really reflect the nature of the particle. If this is the solution for the free particle, if this is what free particle which is moving if this is the wave function which is representing the free particle which is moving, then let us find out the density for this wave function. What is the density of the particle would be? That is going to be x t absolute square, which is nothing but a square. A is independent of time. So, density is becoming independent of time. Density is becoming independent of time. And this is a big problem, a strange consequence. Why it is strange consequence? We have been saying that in quantum dynamics, if anything moving in quantum mechanics, its density should change as a function of time. And if density is not changing as a function of time, then there is no effective motion which we should observe. So, in order to observe any evolution, time evolution or dynamics or motion of a particle in quantum mechanics, its density should change as a function of time. On the other hand, what we see here, if I consider this as a solution of the particle, how does that particle look like then? A particle look like this. This is the particle in quantum mechanics, and this particle does not have change in density. So, we are saying that it is a particle which is moving in one dimensional space, which is moving with a particular momentum velocity, but on the other hand we are saying that density is not changing. It is totally contradicting. So, it is a strange consequence, we cannot accept this. Second strange consequence is following. Let us normalize this wave function. For quantum dynamics, to explore quantum dynamics, the first step is to use a normalized wave function that we have been saying for in the last module. So, this is the normalization condition. If we try to normalize it, what I get? A square minus infinity to plus infinity dx equals 1, which is giving me a equals 0. So, the moment I try to normalize the wave function will vanish. A equals 0, everything is 0. How come a wave function would be 0 and which will represent a particle in quantum mechanics? So, this is another problem with this solution. The third problem with this solution is following. We have already explored that Vp, velocity of the particle. We said that the quantum particle is travelling with this velocity Vp, which looks like this. This is my quantum particle, a wave, nothing but a wave, matter wave, and its velocity is h cut k by 2m. That is called phase velocity. So, this is the velocity of the particle we are saying. On the other hand, we can calculate the momentum, and momentum we have already calculated to be h cut k, or velocity is going to be then h cut k by m. So, two different calculations of the velocity is giving me entirely two different results. A single particle travelling on one dimensional space with two different velocities. How come it is possible? So, these are the three consequences which we have. They are strange and cannot be accepted as the free particle. So, whatever I have presented, that a particle in quantum mechanics should look like this, a plane wave, is still not correct. In order to realize the particle in quantum mechanics, I said that the particle in quantum mechanics is going to be a localized matter wave. This is called particle. So, localized matter wave, there will be wave, but it has to be localized, which means that there will be wave, nothing, 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 then something localized. This is quantum particle. This is the way we have to represent the quantum particle, and this is called nothing but wave packet. So, in quantum mechanics, whenever I want to say particle, just like let us say two hydrogen atoms are bonded through a chemical bond and forming H2 hydrogen gas. Each one can behave as a particle, and should we draw like a dumbbell like this? No. In quantum mechanics, we have to draw like this way. Each particle is a localized wave, and what kind of wave they are? They are actually matter wave, the localized matter wave. One matter wave localized here, another matter wave localized here. So, wave packet is the correct terminology for the particle in quantum mechanics. And how do we create the wave packet? It is just like the optical pulse which we have created previously in the first module, and the same figure I used to represent the optical pulse. I can use the same figure to represent the wave packet as well. So, let us find out the meaning of this wave packet. To eliminate all the strange consequences of the previous analysis, the general solution to the time dependent Schrodinger equation of a free particle should be given by a linear combination of the plane wave solutions. And so, I should have at least two matter waves interacting, because without this interaction I cannot localize a wave. So, this localization of the matter wave occurs due to the interference of more than one matter waves, and when they interfere, there will be a position where they will magnify its strength, there will be a position where they will destroy its strength. They are pulling out in opposite direction, and here they are actually magnifying, and that is why out of phase part will have no contribution, in phase part will have a maximum contribution, and that is the way we can localize the matter wave in space, and this is the correct representation of a particle in quantum mechanics. It is not like a ball moving in one dimensional space. It's not like that. It is a classical picture. This ball moving is a classical picture. Wave packet is the quantum mechanical picture. In the wave packet, this kind of superposition of matter wave is called wave packet, and which exhibits non-zero amplitude in small region like this region, and close to 0 elsewhere, and that is the way wave packet is localizing the matter wave. So, we will try to understand mathematically, and what we will do exactly, we will follow the same thing. Here I will write down that optical pulse. What is optical pulse? We have presented in the first module. Optical pulse is localization of electromagnetic wave in time. That is called optical pulse. On the other hand, this Wavepacket is localization of matter wave in position space, and such a localization can be realized with the help of interference of at least two waves. So, we have taken these two waves, slightly different energies E1 and E2, they are propagating along the same direction. Because E1 E2 are different little bit, that is why K1 and K2 are different, because K depends on its kinetic energy. And we will say that due to this interference, there is an average value I am getting, that is E naught plus delta E plus minus delta E. Another one is K naught plus minus delta K. So, what we have here is this K1, I will assume that K1 equals K naught plus delta K, some average value plus delta K, that is the difference, and K2 equals K naught minus delta K. This is just this will, if I represent this way, it will just simplify the mathematics. Similarly, E1 equals E naught plus delta K, delta E, and E2 equals E naught minus delta E. This is the way we are going to present. In the end, what we are showing here is that these two plane waves having slightly different energies, that is all. And we are now representing those energies with respect to some average values. So, this is, let us say, average value of E naught, the resultant value. My E1 was here and this is E2, and this difference is delta E. That is the basic idea. With respect to certain average value, we are presenting it. So, if we have that and if we plug that in here, then Wavepacket, actual Wavepacket is superposition of those two functions, which will be represented by a linear combination of these two wave function. We will look at this linear combination of this wave function in the next session.